Imagine trying to train a robotic arm in a simulated environment where gravity, occasionally just reverses.
Right, or where a metal gripper randomly phases right through a solid wooden block.
Yeah, exactly. Or where a cup you just pushed somehow remains completely static in midair while your robotic arm teleports through it.
Which is, that's essentially the nightmare you get when you try to use foundation video models like Sora or Juan as world simulators for embodied AI.
It's just a mess. So welcome to AI Paper Slump. We are jumping straight into a massive new paper from Peking University and NVIDIA today.
Yeah, it's called PhysisForcing, Physics-Reinforced World Simulator for Robotic Manipulation.
And for the AI researchers and ML engineers tuning in, here is your high-yield summary. General domain video generation models basically fail as robotic simulators because they generate physically impossible interactions.
Right, the object deformation, the discontinuous trajectories, all of it.
Exactly. So PhysisForcing solves this by introducing a highly scalable training time framework that enforces hierarchical physics alignment.
Specifically, it computes a pixel-level trajectory loss and a semantic-level token relation loss.
And it applies them exclusively on what the authors call physics-informative regions. This dramatically improves base models like 1, 2.2, and Cosmos 3, and get this, without adding a single flop of inference overhead.
Which is the holy grail for this stuff, honestly, and actually improves downstream, closed-loop robotic policy success.
So our mission today is to unpack exactly how PhysisForcing mathematically enforces these constraints in the DIT latent space, the diffusion transformer latent space, and why this is a massive leap toward useful world models.
Because the gap between visual fidelity and mechanical reliability is like the defining bottleneck in embodied AI right now.
Oh, for sure. We have video generation models that can render, the exact reflection of a window on a shiny metallic cup.
Yeah, but they fail utterly at predicting what happens when a robotic gripper applies actual force to that cup.
Right. And if you are using synthetic video rollouts to train a downstream robotic policy, the generated dynamics have to be mathematically and physically valid.
Exactly. The authors point out that current models, even the ones heavily fine-tuned on pure robotic data sets with reconstruction objectives, they suffer from two distinct categories of physical failure during contact-rich manipulation.
Okay, let's break those down. The first category being local dynamic errors, right?
Yeah, this is the obvious glitching. So the model predicts a discontinuous gripper trajectory where the arm teleports between frames.
Or you see object penetration where the fingers of the robot clip straight through a solid object.
Right, or anti-gravity motion where an item just floats for literally no physical reason.
And then you have the global relational errors, which honestly seem a lot more insidious.
They really are. A local dynamic motion might look perfectly smooth in isolation, like the arm moves seamlessly across the frame, but the interaction causality is completely broken.
So like a grasped object might suddenly start drifting away from the gripper.
Exactly. Or a pushed object remains entirely static while the manipulator phases past it. The pixels are moving continuously, but the physical relationship between the objects is just completely hallucinated.
Okay, let's unpack this. Because my immediate instinct as an ML engineer looking at this would be to push back and say, well, if we are training these models on millions of high-quality robotic videos, shouldn't they just, learn physics organically?
You'd think so, right? Like if a model observes a cup being pushed 2 million times, a standard reconstruction loss should force it to predict the cup moving.
Right, it should just absorb the Newtonian mechanics from the data. But I guess it's like trying to learn the rules of chess just by looking at millions of slightly blurry photographs of chessboards.
That's a perfect analogy, yeah. You might figure out what a knight looks like or that it sits near the edges of the board.
You could render the horse shape perfectly.
Right, but no matter how many static photos you reconstruct, you will never fundamentally deduce the rigid L-shaped movement rule. You need a different kind of supervision.
And that's why existing methods fail, right? Because general models lack robotic data exposure and geometric constraints only fix local motion.
Exactly. And the post hoc solutions in the field, like preference-based alignments, DPO or GRPO, they fall short too.
Because they're just, human or AI judges ranking video outputs?
Right. They provide incredibly weak, sparse localization. They tell the model, hey, this video is physically bad, but they don't provide dense gradients explaining that the physics failed specifically at pixel coordinates X and Y.
Makes sense. So if uniform training dilutes the physical signal, the logical next step is isolating the specific pixels that actually dictate the physics.
Yes, we have to figure out how PhysisForcing isolates the physics-informative regions.
Which means building a spatiotemporal physics mask. But you can't just use a simple motion mask, right?
No, because if you only look at moving pixels, you might end up allocating all your loss capacity to, like, a fan spinning in the background.
Or just simple camera jitter.
Exactly. To avoid that trap, the framework uses a highly targeted two-step pre-processing pipeline. First, they deploy CoTracker 3.
CoTracker 3, that's the off-the-shelf, transformer-based point tracker, right?
Yeah, with factorized spatiotemporal attention, it is incredibly robust at tracking dense temporal trajectories across long video sequences.
So it finds where the real sustained motion is happening over time.
Right, but motion alone isn't enough to isolate the robot and the target object, so they pair the CoTracker 3 data with depth anything v2.
Ah, okay. And they run that depth estimator specifically on the first frame of the video, right?
Yes. By taking the inverse of the relative depth, they derive a heavy weighting for foreground objects.
So when you multiply the local motion magnitude from the point tracker by the foreground away from the depth estimator, the background noise just drops out.
Completely zeroed out, the spinning fan in the corner is ignored.
So for the ML engineers tuning in, think about this in terms of your supervision budget. We have a finite amount of loss capacity to backpropagate.
Right, you don't want to waste it on the static texture of a wall.
Exactly. Instead of penalizing the model for slightly messing up the background, we generate a binary mask that exclusively targets the manipulators, the objects, and the points of contact.
We take all our computational budget and aim a laser pointer right at the exact coordinates where the robotic gripper is actively touching the cup.
I love that. And this binary mask is projected onto every single frame to form a contiguous spatiotemporal mask.
Which is the bedrock of the entire framework. We now know definitively where the physical interactions are occurring.
Okay, but knowing where the pixels are moving is only half the battle, right? Because a diffusion transformer operates on a high-dimensional soup of latent tokens, not raw 2D pixel masks.
Exactly. So how do you map a 2D pixel mask into a meaningful structural constraint on a latent representation?
Right. How do we move from the where to the how? Let's get into the math of the dual losses, starting with the pixel-level trajectory alignment.
So the goal here is to fix the local dynamic errors, the teleporting grippers. They extract a hidden feature representation from an intermediate block of the DIT.
Let's call that hidden feature H.
Sure. They pass H through a very lightweight multi-layer perceptron to project it into a specialized tracking space.
And CoTracker 3 gives us ground truth 2D point trajectories starting from the first frame.
Right. So to align the DIT with this, they set up an attention mechanism inside the loss calculation. They use the refined DIT feature from the first frame as the query.
And the DIT features from all the subsequent frames act as the keys.
Yes. For a specific query point on the first frame, you compute a similarity map against every spatial location in frame T.
By calculating the dot product between the query and key features and normalizing it over the spatial dimension using a softmax operation.
Exactly.
But wait, from those softmax probabilities, how do we get a specific XY coordinate to compare against our ground truth? Because you can't just take the argmax.
Right. Argmax isn't differentiable, and we have to backpropagate this loss.
So they use coordinate expectation. You take the softmax probabilities, multiply them by their corresponding spatial coordinates on the grid, and sum them up.
That summation gives you a fully differentiable predicted 2D location for that specific point, generated entirely from the DIT's latent space.
That is so clever. And then you just run a masked mean-squared error loss against the CoTracker 3 ground truth trajectory.
And crucially, you only calculate this loss for the points where our physics mask is active.
So you mathematically force the latent representation to track continuous local motion. That fixes the discontinuous trajectories.
It does.
But this invites a major pushback. If we know exactly where the pixels are moving with a trajectory loss, why do we need the second loss? Why introduce this semantic-level physics alignment with VJIPA?
What's fascinating here is that continuous motion does not equal physical causality. To use a linguistic analogy, the pixel-level loss ensures that all the words in a sentence are spelled correctly.
Okay, so motion is smooth, there are no typos in the trajectory.
Right. But spelling a word correctly doesn't mean the sentence has valid grammar. The semantic-level loss ensures the grammar of the physical world makes sense.
Ah, I see. Because if a robotic arm closes its gripper around a block and moves left, the pixel loss just ensures the pixels of the arm move left smoothly.
Exactly. It doesn't inherently understand that the block must also move left because it is physically constrained by the gripper.
It treats the arm and the block as two separate, well-spelled words without understanding the causal link in space-time.
Yes. To teach the model that grammar, PhysisForcing brings in a frozen video understanding encoder, specifically VJBPay2.
Vision Joint Embedding Predictive Architecture, which is fascinating because it's a self-supervised model.
Right. It isn't trained by reconstructing raw pixels. It predicts masked spatiotemporal feature targets in a latent space.
So its internal tokens naturally develop highly object-centric representations. It just natively understands the correlation between a gripper and a block during a grasp.
So to force the DIT to inherit that, they take that same intermediate DIT feature, pass it through another MLP, and pool it to match VGPay2's token layout.
But they don't align the absolute features directly, do they?
No, that would be a disaster. A DIT generates video by denoising latents, while VJPay2 builds a compressed semantic representation. Direct feature matching would wreck the generation quality.
So how do they do it?
They align the relations between tokens. They take all the tokens under the physics mask and compute a pairwise cosine similarity matrix.
So you get a matrix representing how strongly every physics-informative token relates to every other one in the VGPay2 space.
Exactly. And then you compute the exact same pairwise token relation matrix for the DIT features.
And the semantic level loss is just the distance between those two similarity matrices. Wow.
Right. The ablation studies confirm this perfectly. The pixel loss mostly fixes trajectory discontinuity, while the semantic loss repairs broken global contact, like dropping objects. They are highly complementary.
This is incredible in theory, but let's talk about the technical implementation, because for the ML engineers listening, integrating new losses into foundation models is usually a compute nightmare.
Yeah, but they deployed this on major backbones like WAN 2.2, I2V, A14B, and Cosmos 3 Nano.
Let's look at WAN 2.2, since it's a 14 billion parameter mixture of experts model.
Well, in WAN 2.2, the experts are specialized along the diffusion time step. You have a high noise expert that operates early on to lay down the global layout and macroscopic motion.
And then the low noise expert refines the high frequency appearance details.
Right. And the brilliance here is they only fine-tune the high-noise expert.
That makes total sense. The physical structure, whether the robot is gripping the cup or clipping through it, is committed during those early high-noise steps.
Exactly. You don't need to waste GPU hours teaching the low-noise expert about Newtonian physics. It just renders the metallic sheen.
And for Cosmos 3 Nano, they trained it via LoRa at 720 BP. But what about the inference cost?
Zero. It adds absolutely zero latency or cost during inference.
Wait, really? Because of all the auxiliary models?
Right. CoTracker 3, Depth Anything, VJPA, they are only used to calculate the loss during training. Once training is done, you discard them.
So you get a physically aligned DIT that runs just as fast as the base model. That is huge. Now, there's one more architectural detail. Where exactly in the network is this loss applied?
If we connect this to the bigger picture, they ran a sweep across the WAN 2.2 blocks and found that layer 15, the middle of the network, is the optimal sweet spot.
Why not apply it at the very end, like layer 25, where it has all the information?
Because late blocks are too specialized in predicting final noise, it's incredibly difficult to steer the structural latent space there.
And if you apply it too early, the blocks only contain shallow appearance features. They haven't built the semantic geometry yet.
Exactly. Layer 15 is where it has structural understanding but hasn't rigidly committed to the final noise prediction.
Okay, so we've built this zero inference cost framework. Let's look at the empirical results. Does it actually work on the benchmarks?
The improvements are massive. On our bench, which measures physical semantic plausibility, PF Cosmos hits 63.8.
That's a 9.2% jump over base Cosmos 3, right? Beating WAN 2.6 and VO 3.1.
Yeah, and PF1 jumped 22.3% over its base model.
They also ran it on EZS bench for zero shot out of distribution generalization, and it crushed it there too.
But making the video look right is only half the battle. It has to be useful for downstream robotic action modeling.
Right, the so what factor. We aren't just making pretty videos, we are generating synthetic training data for robots.
Exactly. Under the World Arena Action Planner protocol, injecting PhysisForcing raised the closed-loop success rate from 16.0% to 24.0%.
Beating WOW, the strongest baseline.
And on FastWAM downstream policies for contact-rich tasks, like placing a cup or pressing a stapler, the success rate climbed from 68.2% to 72.8%.
Because if a model generates training data where a gripper phases through a stapler, the downstream policy receives invalid state transitions.
By enforcing boundary constraints, PhysisForcing provides a learnable simulation of reality.
This is huge. Before we wrap up, I want to pose a broader question for you. As foundation models scale, they will naturally absorb better physical priors through sheer volume. But considering all this, will they ever truly internalize Newtonian mechanics without explicit structural constraints like PhysisForcing.
It is the central conflict right now. Will we eventually need to merge DIT architectures with actual physics engine simulators at the latent level? PhysisForcing shows that injecting explicit mathematical constraints is vastly more efficient than just hoping a model memorizes physics.
It forces the model to actually learn how the knight moves, rather than just endlessly rendering the chessboard. So for everyone tuning in, think about how you might apply hierarchical token alignment in your own ML architectures. Thank you for joining us on AI Paper Slop, and we will catch you on the next deep dive into the research.